Look at the blueprints of any modern skyscraper, and you will see perfect right angles and exact geometric calculations. But drop below the ground line, and that architectural certainty vanishes. Humanity designs rigid, mathematically precise structures, yet we are forced to build them on top of a highly variable, multi-phase, and unpredictable natural material. The Earth does not arrive with a structural specification sheet. To resolve this physical disconnect, civil engineering relies on a specific set of principles. In the university curriculum, this is codified as course AMJ20504 Soil Mechanics. This animated diagram demonstrates the engineering solution to unpredictable dirt. We take a chaotic natural environment and force it into a controlled, analyzable geometric model. The 15-week syllabus for soil mechanics operates as a precise mathematical algorithm. It provides the exact sequence of steps required to build a functioning physical model of the ground from first principles. The progression is strictly chronological. Engineers beginning week 1 by observing the static properties of geological rock deposits. By week 15, they are evaluating complex, time-dependent structural failures involving massive concrete loads. The structural steel above ground is only as stable as the equations calculating the dirt below it. Understanding that soil is the foundational computational challenge that dictates whether modern infrastructure stands or falls. The curriculum opens its first phase in weeks 1 and 2 with basic geology. Before applying mathematics to a site, engineers must classify the origin and mineral makeup of the solid particles they are building on. Moving into week 3, the focus shifts to basic characteristics. Geotechnical engineers never evaluate a patch of ground as a single uniform material. They analyze it as an interacting 3-part system. This requires establishing the phase relationship. The phase relationship is a mathematical framework that quantifies the exact volumetric proportions of solids, liquids, and gases within a given sample of soil. In this cross-section, you can see how the soil block separates into distinct states of matter: solid rock at the base, liquid water occupying the middle, and empty air volume resting at the top. Discovering the exact ratio of these 3 phases requires physical extraction and laboratory testing. Specifically, engineers rely on sieve and hydrometer analysis, a set of physical procedures used to measure the exact particle size distribution of both coarse and microscopic grains. Here in this historical illustration, we see the early fluid dynamics apparatus scientists originally designed to analyze how microscopic particles settle in suspension, the very foundation of modern hydrometer testing. Once the laboratory extracts these precise particle sizes and phase ratios, the data is fed into the British and Unified Soil Classification Systems. This translates local, irregular dirt into globally standardized material categories. Looking at the syllabus document, this initial sequence maps directly to course outcome 1. At this stage, students are required to reach cognitive level C3, which tests their ability to apply basic, known theories to these classification systems. Until you have definitively quantified the exact ratio of rock, water, and air beneath a structure, it is physically impossible to predict how that structure will behave once constructed. By week 6, the syllabus introduces seepage. The static model is now subjected to civil engineering's most disruptive variable, water. This simulation illustrates the reality of the underground environment. Water aggressively courses through the microscopic porous gaps between tightly packed, rigid grains of soil. To calculate this movement, engineers measure permeability. Permeability is a metric that defines exactly how easily a fluid can travel through the interconnected voids of a specific soil matrix. Because this underground movement is invisible from the surface, engineers must visualize and calculate the fluid's path by constructing flow nets. Flow nets are graphical representations of 2-dimensional seepage, built using intersecting flow lines. In this 2D cross-section of a dam, the animated grid appearing in the soil demonstrates a completed flow net. It allows engineers to mathematically map the directional vectors and pressure drops of seeping water beneath massive structures.
Mapping this fluid pressure brings us to week 8, stress distribution. The calculations performed in this week represent the conceptual pivot point for the entire 15-week curriculum. This pivot relies on calculating effective stress. Effective stress is the actual pressure that soil particles exert physically on each other, calculated by subtracting the internal water pressure from the total downward weight of the earth. The core physics dictate that as water flows through the voids, its upward pressure actively counteracts the downward gravitational weight of the solid soil particles. Watch the flow net beneath the dam. The red arrows showing upward water pressure increase, actively forcing the white friction arrows between the solid grains to shrink. This seepage pressure directly reduces the internal friction holding the dirt together. Water is an active, destabilizing force. Its movement through the ground dictates the structural integrity of the foundations resting above it. Entering Phase 3 of the syllabus in weeks 10 through 15, the curriculum introduces the high-stakes outcome of unchecked stress, mechanical failure. This animation shows what geotechnical failure actually looks like. A heavy foundation slips, the ground fractures, and the structure violently tilts along a diagonal plane. This visual is the subject of Week 10, shear strength. Soil rarely fails by simply compressing downward. It fails by tearing apart and sliding along specific mathematical slip planes. Calculating the critical breaking point of these slip planes relies on mastering the Moore-Coulomb models. The Moore-Coulomb model is a mathematical failure criterion that predicts how materials will shear under specific combinations of normal and shear stress. But failure isn't always immediate. Transitioning to Week 13, the syllabus introduces consolidation theory, bringing in the final variable of geotechnical engineering, time. Ground settlement is rarely instantaneous. It is a slow process, sometimes spanning decades, driven by the massive weight of a building gradually squeezing water out of the microscopic soil voids. This historical portrait shows Carl Terzaghi, the engineer who first deduced the mechanics of this time-dependent sinking process and developed one-dimensional consolidation theory. By applying Terzaghi's theory, modern engineers calculate the specific rate at which water will be expelled, allowing them to predict exact foundation settlement rates over a 50 or 100-year lifespan. Reaching this predictive capability satisfies course outcome 2. At this point, the student graduates to cognitive level C5, proving they can evaluate and solve complex, time-dependent civil engineering problems. True engineering mastery requires mathematically predicting exactly when a material will deform under prolonged stress long before the first concrete is poured. To understand how these theories are enforced, we have to pull back from the physics of the soil and look at the pedagogical architecture of the syllabus itself. This assessment distribution table reveals a strict division of competency. The grading structure is explicitly split between a 60% final exam and 40% continuous assessment. The 60% final exam serves a highly specific function. It strictly tests the mathematical and theoretical modeling covered in the first 2 course outcomes. The remaining continuous assessment relies on physical lab work executed in Week 8. Panning up to course outcome 3, we see these lab reports are the sole mechanism used to assess a student's ability to analyze experimental results. Theoretical mathematics are useless in the field without the empirical, messy data generated by physical lab work. Theory must be anchored by physical measurement. Zooming out, this grueling 15-week academic progression serves an ultimate, global purpose that extends far beyond this single university classroom. Here in the United Nations General Assembly Hall, global targets like Sustainable Development Goal 09 are set. This goal mandates the creation of resilient global industry, innovation, and infrastructure. Delivering on that global mandate, whether building hydroelectric dams or super tall skyscrapers, relies entirely on engineering students mastering these exact geotechnical principles every single year. Society can only safely build upward toward the sky if it first possesses the mathematical algorithms required to master the earth below.